Hello, let's continue our discussion about hybridization. And let's talk about the hybridization of 5 and 6 electron domains. And so let's look at a molecule like PCl5. Its Lewis structure looks something like this. Is trigonal bipyramidal, both electron domain geometry and molecular geometry. We've got the 3 chlorines that are equatorial and have bond angles of 120 degrees. Then we have the axial chlorines, and those bond angles are 90 degrees from the equatorial positions. And so we need to come up with 5 hybrid orbitals. We need 5 hybrid orbitals. So phosphorus is in the P block, and it's got a neon core, 3s2, 3p3. And because it's in the P block, it also has empty 3d orbitals that we're going to use to make our hybrid orbitals. So we're going to take the 3s, the 3p, and these empty 3d orbitals. So the 2 electrons in the 3s2, an electron in each of the 3p orbitals. We're going to promote an electron from the 3s up to one of the 3ds. So it takes a little bit of energy to do that, to unpair it. And then we can gain that energy back as we hybridize. And that now we're going to have 5 hybrid orbitals by combining the 3s, 3p, and 3d, each with a single electron in them. And we're going to have 4 unhybridized 3d orbitals. There are 4 of those. And so we have sp3d, sp3d. We got 5 of those. They're equivalent. They allow us to have the electron domain geometry that we want. They're all degenerate. And so now those sp3d orbitals can overlap with p orbitals from the chlorine to give us our molecular structure. So now let's see how that looks. We've got our phosphorus that's got these 3 equatorial, we could call them that, sp3d hybrid orbitals. And these 2 axial sp3d hybrid orbitals. Now, I've greatly simplified the drawings for these. These really have multiple lobes. A small lobe on the opposite side of where you see these big lobes. So look in your book at those pictures to get that. And we've got a chlorine that's coming in, was unhybridized orbital, p orbital, and those are the 3p orbitals that have a single electron in them. And so if you wanted to, you could look at it, the p orbital have an electron and the chlorine bringing an electron. And so that gives rise to our 120-degree bond angles that are equatorial. There are 90-degree bond angles between the axial and equatorial positions. So that's sp3d, 5 hybrid orbitals. So let's look at the case when the electron domains equal to 6 around our central atom. Something like sulfur hexafluoride. And we're going to do a very similar process to what we just did for sp3d. Our sulfur has a neon core, 3s2, 3p4, but it's got these empty 3d orbitals that we can use. So here's my 3s, my trio of 3p orbitals, and my quintet of 3d orbitals. So we got 2 electrons in 3s, and 1, 2, 3, 4 electrons in my 3p. Have these empty 3d. We want to promote. So 3d, 3p, 3s. We're going to unpair those electrons that are in the filled 3s and 3p orbitals, and we'll promote them up to the 3d. Cost us energy, but then we can get it back when we hybridize. And so now I'm going to have 6 hybrid orbitals, and what's left over are a trio of 3D unhybridized orbitals. That the number of orbitals has to be conserved. What we start out with has to be the number we ended up with. So we start out with 9 unhybridized orbitals between the 3s, 3p, and 3d, and now we've got 9 orbitals. When we're all said and done, 6 of them are hybrid, 3 of them are unhybridized. And so now we've got 6 electrons. They can put an electron in each of those hybrid orbitals. These are sp3d2 orbitals. sp3d2. And that those superscripts are telling us how many of those particular orbitals we're using. We're using a single s, we're using 3p, a trio of p's, and a duo of d's. And so here's our sulfur. Once again, I'm going to only draw the large lobe of these. All these really have double lobes to them. And so this is really three-dimensional, and all of those bond angles are 90 degrees. And if you want to think of them as bringing in an electron apiece, and then my fluorines have their trio of p orbitals. One of them has a single electron. So there's a fluorine. Here's a fluorine. Here's a fluorine. Here's a fluorine. Here's a fluorine. And last but not least, this fluorine with his p orbital that only has 1 electron in it. So they each bring in an electron, they're sharing them. Covalent bonds gives us an octahedral electron geometry, electron domain geometry, and an octahedral molecular geometry. For all those bond angles are 90 degrees, we've got these 6 hybrid orbitals that we've used to create this molecule, or explain the bonding actually. these atoms don't know that they're hybridizing. These electrons don't know where they're going. They just do that, and this is how we go about explaining it through this hybridization theory.